right. Thank you, everyone, for joining us again for our monthly PCAST talk. Before we get into today's talk, we just have a few update slides from the project. So a little bit of news. So PRIMA has been active at a lot of conferences. So we're excited to have been a big presence at the most recent summer AAS, as well as having multiple papers presented at SPIE this summer. We even had one of our co-Is, Kara Battersby, giving a plenary talk at AAS and gave a shout out to PRIMA. We also, of course, a couple months ago finished our site visit. And so we had a big sort of week-long all hands on deck with the whole team, which culminated in one day with the review panel coming and seeing us, sort of letting them see how ready PRIMA is to go and how much the whole team is behind it. So we were really excited to have that. You can read more about updates that are going on in our summer newsletter as well, which should be posted on the website shortly. So we have some upcoming talks, especially some upcoming talks on the PI science cases. So coming up in August, so next month, we'll have Irene Chivai. And so she will be talking about some of the work studying dust and the evolution of metals. And then in October, we'll have Andrea Benzati, and he will be talking about protoplanetary disks. So today, of course, we're all here to hear from Takuya Hashimoto. So he will be telling us about Green Pea galaxies and some science cases that would be motivating future PRIMA work.
All right. Yeah, thank you, Betsy, for the introduction. So let me try to share the screen. Can you see my slides?
Looks great. Thank you.
Yeah. Okay. So sounds great. So, all right. So first of all, yeah, I'd like to thank the organizers for giving me this opportunity to present our proposed science case for PRIMA. So in this talk, I will first introduce galaxy formation and evolution and cosmic reionization. And then I will present recent high redshift studies, mainly from our group using both ALMA and JWST. And finally, I will explain the current limitations and how PRIMA can overcome them. Yes, so the schematic picture shows the evolution of the universe from the Big Bang to the left and present to the right. And as you know, the cosmic reionization is the final phase transition of the universe from a neutral state to the ionized state. And it is widely thought that it started around redshift of 20 and ended at around redshift of 6. And it is widely thought that the first stars and galaxies produced a large number of hydrogen ionizing photons. And some of these photons escaped into the surrounding intergalactic medium, the IgM, and gradually reionized it. And hydrogen ionizing photons, also called Lyman-continuum photons, have wavelengths shorter than 912 angstrom or energies higher than 13.6 electron volts. The key questions here are how and when cosmic reionization proceeded. To answer these questions, it is important to understand the Lyman-continuum escape fraction, which is still highly uncertain. Because Lyman-continuum escape is regulated by the properties of the interstellar medium, or ISM, we need to study these properties through spectroscopy. So this shows a modeled spectrum of a distant galaxy from the rest flame UV and optical to the far infrared. And ALMA plays an important role in the spectroscopy of high redshift galaxies because rest flame far infrared emission lines are redshifted into the submillimeter regime, where they can be observed with high sensitivity by ALMA. As with optical emission lines, combinations of far infrared lines allow us to examine key physical properties of galaxies, such as the star formation rate and important properties of the interstellar medium. And far infrared lines also have the advantage of being less affected by dust extinction than optical emission lines. Right, so this schematic picture shows the ISM of a galaxy, including H2 regions and photo-dissociated regions, PDRs. And these far infrared emission lines have been observed in many nearby galaxies with ISO, Akari, and other facilities. It is now also possible to observe them in high redshift galaxies with ALMA and NOEMA. And this table lists the critical density and ionization potential for each transition. For example, C2 has an ionization potential of about 11 electron volts and can be emitted from both H2 regions and PDRs. On the other hand, O388 micron has a higher ionization potential and traces ionized regions around young massive stars. Sorry. Sorry. And because the 2 or 3 have different critical densities, we can also estimate the electron density from their line ratio. Okay, so this is a summary of far infrared line observations in the distant universe. Carbon-2 on top is often detected in high redshift star-forming galaxies and quasars, thanks to several large ALMA programs targeting this line, like Alpine, ALX, and Rebel's large programs. And there are now more than 100 detections beyond redshift of 4. And in addition to Carbon-2, since the late 2010s, the O388 micron line has also been actively targeted at high redshift. Following the detection of the most distant emission line galaxy known at that time in 2018, this line has now been detected up to redshift 14. And this box summarizes the current status of high redshift spectroscopy with ALMA. There are also a few detections of another important O352 micron in star-forming galaxies, in a few star-forming galaxies at redshift of 6 to 7. And also the oxygen-1 lines probe warm and dense neutral gas, and they have recently been detected in galaxies or quasars in the Epoch of Reionization. And another interesting result is the detection of the OH 190 micron absorption line in high redshift SMGs and quasars with ALMA. So the OH 119 micron absorption line is particularly useful for studying molecular gas outflows. And it is widely thought that strong outflows can suppress or even quench star formation. So therefore, it is important to measure both the presence of and the velocity of the outflow. And from the blue shift of the absorption line, we estimated a molecular gas outflow rate in this quasar, which is about 2. This suggests that outflow may eventually terminate its star formation activity. Although this study focuses on a quasar, I'd like to stress that outflows may also play an important role in the Lyman-continuum escape. And this is because outflows can create holes or low-density channels in the interstellar medium, allowing Lyman-continuum photons to escape more easily. All right, so this is the result from Herschel dwarf galaxy survey data. This is the stacked spectrum of carbon-2 158 micron of 29 galaxies. So according to these authors, they have shown that the carbon-2 has a broad wing component, which is attributed to the presence of outflow. And because PRIMA high resolution mode has the spectral resolution higher than the Herschel, so we can also try to examine the presence of carbon-2 broadwing using PRIMA Fires, right? So one striking result from ALMA studies is that high redshift galaxies often show high O388 micron over carbon 158 micron luminosity ratios. So this figure shows that the ratios in high redshift galaxies filled large symbols are generally higher than those in nearby galaxies shown in red crosses or gray small dots. Sorry. Several explanations have been proposed for these high ratios, including a high ionization parameter, a low covering fraction of neutral gas, and a high oxygen to carbon abundance ratio. Although there are several possible explanations, these high ratios provide important information about the ISM of high redshift galaxies, and they may also be related to Lyman-continuum escape. In particular, a high ionization parameter or a low neutral gas covering fraction may allow Lyman-continuum photons to escape more easily into the surrounding IgM. And indeed, theoretical studies such as Katz et al. 2022 also predict that far infrared luminosity ratios can be used to constrain the Lyman-continuum escape fraction. And on top of in addition to these, joint ALMA and JWST studies also suggest that some high redshift galaxies show unusually strong O388 micron emission. And this figure shows an O3 diagnostic diagram constructed using PINEB models. Here we assume that all the oxygen-3 emission comes from homogeneous gas with a single electron density and temperature. And here the y-axis is mainly sensitive to the electron temperature because oxygen-3 4364 angstrom is the auroral emission line, while the x-axis is sensitive to both the electron temperature and density because 88 micron is fine structure emission line. The field symbols here represent high redshift galaxies. And interestingly, some of the observed far infrared to optical O3 line ratios lie outside of the model grid and cannot be explained by the simple one-zone model. In particular, the oxygen 388 micron to 5008 angstrom line ratio is too high for the electron temperature and density independently determined from the JWST data for these galaxies. And we interpret this as evidence that the ionized gas has multiple density components rather than a single uniform density. Although I will not go into the details, our theoretical calculations show that a two-zone model can reasonably reproduce the observed O3 line fluxes. This schematic picture shows one possible scenario for the two-zone model. In this picture, we have both, the first component has high electron temperature and density, whereas the second model has the low density and temperature. And because 4364 angstrom is sensitive to the warmer, hotter gas, this emission line predominantly is emitted from the component 1, whereas 88 micron must come from low density gas. and oxygen-3 5008 angstrom can come from the both components. In this picture, the ionized gas has a porous structure, allowing ionized photon to leak through low-density channels. And indeed, previous studies of the Large Magellanic Cloud have shown that in such a porous and leaky structure, highly ionized low-density gas can efficiently emit the oxygen 388 micron line. Therefore, if this picture is correct, strong O388 micron emission may indicate a physical condition that allow Lyman-continuum photons to escape. So such galaxies could therefore contribute significantly to cosmic reionization. So ideally, we would like to directly measure the Lyman-continuum escape fraction of galaxies at redshifts greater than 6. However, this is extremely difficult. Lyman-continuum photons are strongly absorbed by neutral hydrogen along the line of sight, as shown in this figure. By the way, this shows the transmission of Lyman-continuum photons at each source redshift. And you can see that the transmission becomes significantly low beyond redshift of about 5. Therefore, many studies aim to establish indirect methods to infer the escape fraction based on correlations with other observable properties in the local universe. And these relations can then be applied to high redshift galaxies to indirectly infer the escape fraction. And one example of such an indirect method uses optical oxygen line ratios. If the interstellar medium is highly ionized, for example, in a density bounded nebula, O3 can become much stronger than oxygen 2. As a result, the O3-2 ratio tends to increase with the Lyman-continuum escape fraction. And this trend has also been found in larger samples and is widely used to estimate escape fractions in high redshift galaxies observed with JWST. However, optical emission lines mainly probe the ionized gas. So far infrared lines, on the other hand, provide an independent probe of both the ionized and neutral gas. And that's why here we propose the far infrared line ratios to infer the escape fractions. So let us now look at the far infrared observations of Lyman-continuum emitters. So far, only a very small number of Lyman-continuum emitting galaxies have been observed in far infrared emission lines. So in this table, I have listed the target name, the redshift, the escape fraction of Lyman-continuum photons, the references, and the references for far infrared observations. For example, Halo 11 was observed with Herschel, but most non-Lyman-continuum emitters were discovered after the after the Herschel mission had already ended. So here I briefly show the Herschel results for Halo 11. The oxygen 3 to carbon 2 luminosity ratios is about 2.5, which is consistent with our prediction. However, we clearly need far infrared observations of a much larger sample of Lyman-continuum emitters. And by the way, this picture shows the image of Halo 11 consisting of at least 3 large knots and halo. And the escape fraction is 3.2%. So as a result, the far infrared properties of Lyman-continuum emitters remain largely unexplored. At the same time, a large sample of Green Pea galaxies, including many confirmed Lyman-continuum emitters, has now been identified. If we can establish a link between Lyman-continuum escape and far infrared line properties, this will significantly improve our interpretation of ALMA observations of high redshift galaxies. Motivated by this idea, we have conducted a pilot study using SOFIA FIFI-LS in 2023. So we observed another Lyman-continuum emitter, Markarian-54, a blue compact dwarf galaxy with an escape fraction of about 3%. We targeted two key far-infrared emission lines, oxygen 388 micron and carbon 258 micron. Here I show the oxygen 388 micron map where we have successfully detected the emission shown in this background color image, and black contours indicate the reciflame optical, this was, I think, SDSS G-band image. So we then investigated the relation between the far infrared oxygen 388 micron over carbon 50 to 58 micron line ratio and other physical properties. And among these, we find that this far infrared line ratio positively correlates with the optical O3-2 ratio, oxygen 3 over oxygen 2 ratio. And since since O3-2 is known to correlate with the Lyman-continuum escape fraction, we can derive an empirical relation between the far infrared line ratio and the Lyman-continuum escape fraction. And the result is shown in the right panel. You can see a positive correlation between the two quantities. And here, importantly, the two galaxies, Halo 11 and Markarian 54, observed with Herschel and Sophia, respectively, can be used to, calibrate this our empirical relation. And if this relation also applies to high redshift galaxies observed with ALMA, strong O3 emitters may have Lyman-continuum escape fractions and could therefore contribute significantly to cosmic reionization. However, there are two important limitations. The current sample is still small, and far-infrared observations are available only for galaxies with relatively low escape fractions. And future observations with PRIMA 5S will overcome these limitations. So our proposed study targets Green Pea galaxies. These galaxies are considered among the best local analogues of galaxies in the reionization epoch. They are especially compact, actively star-forming systems with extremely strong optical O3 emission. Importantly, many Green Pea galaxies have direct Lyman-continuum detections with HST COS, covering a wide range of escape fractions from a few percent to up to 90%. They therefore provide an ideal laboratory to study the connection between far-infrared line ratios and Lyman-continuum escape. Green Pea galaxies typically have, as I said, compact morphologies. Their angular sizes are about 0.1 to 0.2 arc seconds, so they can be treated as point sources for PRIMA. So for the feasibility estimate, we assume a typical Green Pea galaxy at redshift of 0.26 with a star formation rate of 10 solar mass per year. And the expected line fluxes are estimated mainly from our published relations between star formation rate and line luminosity, like Deleuze et al. 2014 and Pereira Santaella 2017. We also assume typical line ratios and gas densities and 20% OH absorption depth against continuum for the estimate of feasibility for the OH 190 micron absorption. Using the phi-rest exposure time calculator shown in the bottom, in the point source mode, several key lines can be detected at a signal-to-noise ratio of 5 in just about 1 hour. These include oxygen 163 micron, oxygen 388 micron, carbon 258 micron, and OH absorption line. The weaker nitrogen 357 and oxygen 145 line might require roughly 10 hours per source. So as an example survey design, we propose to observe 20 Lyman-continuum emitters and 20 non-emitters as a control sample. The total observing time would range from about 80 to 800 hours, depending on the required depth and line coverage. Green Pea galaxies already have extensive multi-wavelength data. For example, HSD COS in the rest frame UV, KEK, VLT, and Subaru in the optical, GMRT, VLA, and GBT in radio, and Chandra in X-ray. So yeah, clearly, this science case has a synergy with a lot of multi-wavelength facilities. And by combining these data with PRIMA far-infrared spectroscopy, we can for the first time construct a unique reference sample for interpreting high redshift galaxies observed with ALMA, JWST, and Chandra, etc. And this sample will also provide important templates for future facilities, such as the ALMA WSU, ALMA 2040, and at last, or LST project, that is a future single dish project that all aim to target the rest-frame far-infrared fine structure emission lines at high redshift. Right. Let me summarize the three main scientific goals. First, we will examine the relation between the far-infrared line ratios and the Lyman-continuum escape, as I have introduced. This will provide an empirical test of predictions from cosmological simulations such as Halley-Katz et al. 2022. So what we need is, because we can directly measure the Lyman-continuum escape fractions from Green Pea galaxies and the far-infrared line ratios, we can empirically examine this relation. And some of you might think that rather than using O3 over carbon-2 line ratios, it might be useful to target O3 over oxygen 1 because it is not affected by the, for example, oxygen over carbon abundance ratio. But yes, indeed, our proposed science case can also do that. And second, we will also investigate the physical conditions of the interstellar medium. For example, we will measure the electron density using the 52 to 88 micron ratio, and also using nitrogen 357 micron, we can also constrain the nitrogen over oxygen abundance ratio, although this emission line can be weaker and hence require significant amount of exposure time. And in light of recent discoveries of nitrogen-enhanced galaxies at high redshift with JWST, it would be also interesting to examine these nitrogen over oxygen abundance ratios in Green Pea galaxies using far-infrared line ratios as well. And in addition to these, as I said earlier, as in the case for a joint analysis of JWST and ALMA, I mean rest frame optical and far-infrared emission lines, combining 3 oxygen-3 emission lines, that is 88 micron, 5008 angstrom, and 4364 angstrom, we can examine the presence of the density stratification, which might facilitate the Lyman-continuum photon escape. And we can do this also in Green Pea galaxies, because most of the Green Pea galaxies have both the detections of oxygen-3 5008 and 4364 angstrom. And third, we will also study gas kinematics and multi-phase outflows using OH absorption line, as well as the presence of broad emission component in carbon-2 158, or even in other emission lines such as oxygen-388 or oxygen-1 emission lines. So by combining these absorption and emission lines, we can also examine multi-phase outflow. And as I said earlier, the presence and the velocity of outflow is also a key for the that facilitate the Lyman-continuum escape. All right, I think I have gone through too quickly, but this is the summary. So let me repeat the key take-home messages. So strong oxygen-3 88 micron emitters might have played a key role in the cosmic reionization. Far infrared line diagnostics provide powerful constraints on the escape fraction, as well as ISM properties and outflows. We propose phi-res observations of 20 Lyman-continuum emitters and 20 control non-Lyman-continuum emitters, for example, that would result in the total exposure time from 80 to 800 hours, depending on the strategy. The survey will also establish a UV, infrared, radio, and X-ray template for among the best local analogues of reionization galaxies, that is Green Pea galaxies. And this dataset will serve as a key calibration for interpreting ALMA and JWST observations of high-Z galaxies, and also serve as a golden template for the future radio missions, radio projects such as ALMA 2, ALMA 2040, and LST at last. All right, thank you very much. That's all.
All right, thank you so much. We have time now for questions. Folks are welcome to ask questions in the chat or go ahead and raise your hand. Go ahead, Alberto.
Takuya, thank you for an excellent talk.
Yeah, thank you.
I was curious, particularly about the explanation of the multi-phase or the stratified nature of the source to explain the 88 micron extra brightness. And can you explain a bit more about how that works precisely?
Yeah, okay.
I mean, I see that the sources where you see these are high temperature, meaning they are low metallicity, since primarily. But yeah. Can you explain me a bit more how this works?
Yes, sure. Yeah. So first of all, let me show again how we think that a single zone interstellar medium model is not appropriate to reproduce some of the high redshift galaxy data points. So these field data points indicate high redshift galaxies observed with both JWST and ALMA. So that's why they have both reciprocal optical plus far infrared O3 emission lines, right? And then the model grid colored color-coded in blue and reddish lines indicate the PINEB model's grid produced assuming a single electron, a uniform interstellar medium with a single electron density or a single electron temperature. And some of these galaxies lie outside of the grid. And actually, they should have, so if we interpret directly from the figure, their electron density should be lower than 1 per cubic centimeter, which is odd, right? On the other hand, actually, all of these galaxies are detected, observed with JWST, and they are detected in the rest of oxygen 2 doublet, 30 to 77, 30 to 30 angstrom, which is a good density tracer. And those indicate much higher electron density, like 50 or up to 1,000 per cubic centimeter. That is one of the reason why we think that the density stratification must be present in some of these high redshift galaxies.
So to summarize, you essentially the low density component is actually the one that explains this displacement to the right in the diagram, and
yeah,
but you still have a high density component because that is required.
Yeah, that's right. Let me try to show my backup slide. Can you see my screen again?
Yes, just small, but
yeah.
Okay, that's better. Yeah.
Yeah. Okay. Great. So now, so here, rather than the log scale, here they are both in the linear scale, and so the data point of a galaxy, high redshift galaxy, is, as I said, outside of the model grid. So in order to reproduce that, we have, as a first easy test, we have introduced two-component model, two-zone model, that ionized gas with different electron density and temperatures. And that in order to reproduce this data set, the intersection should go through the data point like this, right? So although we cannot uniquely determine the exact value of density and temperature for these components, but they should be like this or this. So this indicates that the component 1 should be high density, high temperature gas, and the second component should be low density, low temperature gas. And we have also tried to reproduce the luminosity and so on using the emissivity, volume emissivity, and so on. And then we find that if the volume density of the two component is 300, which is, I understand, very high, I mean, the low density gas is predominant, then we can reproduce all the O3 emission lines in this galaxy.
I see. And the low temperature for this low density phase, what do you think is causing that? Because normally you would think that it's related fundamentally to the metallicity, but maybe not here. Or
yeah, so, that is right. So one possibility is that oxygen 4364 angstrom is the auroral emission line. So it is biased. It can be biased against high temperature gas, right? So whereas oxygen 388 micron can nicely capture even lower temperature gas. And independently, and in another paper by Harikane et al., they have proposed that if this picture is true, the true gas phase metallicity of high redshift galaxies can be could have been underestimated, or in other words, the true gas phase metallicity at high redshift can be higher yeah, if that is the case, the mass metallicity relation can be also changed. So that might be very interesting.
Okay, thank you very much. And
yeah,
I appreciate the explanation.
Thank you.
All right, thank you. We have another question from Margaret Mexner.
Hey, thank you for an excellent talk. First of all, I'm excited to see SOFIA data being published. Yay.
Yes.
I used to work on SOFIA. Secondly, the question I had was, I don't know much about Green Pea galaxies, but are they considered low metallicity? Because your local analogues, like the Haro objects, are all low metallicity dwarf galaxies.
Yes, you're right. So according to the previous observations of Green Pea galaxies using HST COS or KEK, VLT, etc. Yeah, Green Pea galaxies seem to have very low gas phase metallicity, even lower than Herschel dwarf galaxy survey galaxies. And one of the key difference between the HDGS galaxies and Green Pea galaxies is that among the HDGS galaxies, only one galaxy, Halo 11, has been observed in the Resse flame far infrared. On the other hand, Green Pea galaxies will be observed. We can target Green Pea galaxies in far infrared emission lines, and on top of that, most of the Green Pea galaxies have the measurements of direct Lyman-continuum escape fractions. So we can, for the first time, establish the link between the Lyman-continuum escape fraction and the far infrared properties.
Well, very nice. Looks exciting.
Yeah, thank you.
All right. Do we have any other questions? Yes, Alberto, go ahead.
Only if nobody else wants to ask questions. But so concerning the 119 micron OH outflow, which is a very exciting detection. I mean, the fundamental issue with a 119 micron line in OH is that it's very high optical depth, typically. So, in other words, it's very difficult to estimate a mass based on those data. Have you? So, what did you do to try to pull together a mass outflow rate here?
Yeah, right. You're absolutely right. Yes, indeed. There are several transitions of OH absorption lines, and I think you're right. I think OH 190 micron had the highest optical depth, right?
Yes, that's the highest optical depth line.
Yeah, so you're right that we have to assume something about the OH absorption line in order to accurately estimate the molecular gas mass or molecular gas mass outflow rate, mass loading factor, and so on. And yes, you're right. Although I forgot the detailed assumption, what was that?
I mean, don't worry. I can check out the paper. I mean, it gives you an excellent measure for the velocity. That the outflow velocity is just fine. But it's known to be very optically thick in local objects. So, but it's very exciting work. Thank you.
Yeah, thank you. So, for example, although so in this object, in this case, the target is at redshift of 6, and OH 119 micron has been observed and detected in ALMA band maybe 6 or something, which has a high transmission. But maybe we can try to target other OH transitions in this quasar, for example, try to see if that kind of assumption is reasonable or not. And because at this stage, most of the high redshift OH absorption line studies work on this transition, I mean 190 micron. Such kind of detailed study targeting other transitions might be very interesting in the near future. Thank you for your idea.
Well, I mean, it's the next transition is 84 microns, which is, I guess if I did it right, is about 590 microns observed frame. So it may be hard to do, but maybe not impossible. I haven't looked at the transparency of the atmosphere there, but I think it's not great.
All right, well, thank you so much again for your talk today. As a reminder, this will be recorded and it will be available on our webpage and on YouTube. And of course, we invite everyone to join us again next month when we'll be hearing from Irene Shivai. All right, thank you so much.
Thank you.